Okay, so today I'm going to show you how to quickly differentiate functions, which means that you will no longer have to deal with limits. What I'm going to show you will not be boring to solve. Well, I'm not going to lie to you, it'll still be boring to solve, but it'll allow you to get through it quicker. So let's get into it. First, this is probably the method you're used to, right? You're probably taught how to solve derivatives via limits. So right here we have f of x equals x cubed plus 2x, right? So then they apply the definition of a derivative, which is the limit of delta x as it goes to 0, and then you have to do all of this work, right? Now, as you were learning this, you were probably thinking, no way, there has to be a faster way to do this, right? There's always a faster way to do things in math. Well, you are correct. There is indeed a much faster way to do this. So what does differentiation actually mean? Well, according to Merriam-Webster, the development from the one to the many, the simple to the complex, or the homogeneous to the heterogeneous. Now, what does that actually mean? Now, in your instance, when you were learning the limit, you were probably thinking the simple to the complex sounds very true. Well, it is true. However, not in the way that you're exactly thinking. See, what they mean is that you're breaking up something that was a singular function into many parts. So what derivatives actually do is you're taking a function and you're finding each of its individual slopes, if you will. You're finding where the function changes. So say you have x squared, right? The derivative of x squared is 2x. So what that means is the slope of x squared as it's changing, it goes to 2x. Now, I'm not very good at explaining this to you, I'm not going to lie, but we will see more clearly what I mean now in a little bit. Okay, so here we have the function x squared, right, just a standard parabola. Now, the derivative of x squared is 2x. So 2x produces the slope of the tangent line. So this is our tangent line at the origin here. We can find the tangent line at other points by plugging it into this simple equation. Ignore the errors. This is just Desmos being mad that I'm using this as an example. So say for example we have the point 1, 1, right? So if we plug y minus 1 equals our slope, so that'll just be 2, times x minus 1, right? That results into 2x minus 1. So let me turn off this tangent line. So this is our tangent line at point 1, 1. And we can continue to do this for any point on this parabola. And that is the whole point of taking derivatives, is we are finding the slope of the tangent lines. So now here's some things you need to know before we can get started. X to the nth power goes to n times x to the nth power minus 1. This is how it breaks down essentially. So let's do another example, is if we have x to the 6th power, that will instead become 6x to the 5th power. You see what I mean? So we bring the exponent out front and then we subtract 1 from what it was. So we go from x to the 6th to 6x, and then 6 minus 1 equals 5, so then it becomes x to the 5th power. Now, for constants, which would be n in this case, we're just going to assume that for all these examples that I have here, n is just a number. A real number, you know what I mean, all the regular criteria that go with that. So constants always go to 0 if they are alone being added or subtracted. So that is what I mean is, for example, they can't be multiplied or divided. So if we have f of x equals 6, the derivative of f of x is f prime of x equals 0. So no matter the size of the number, no matter the number, if it's negative, positive, a decimal, a fraction, if it is a regular, just plain number, no variables, it will go to 0. Now, here's some things that are a little harder to explain how they get these derivatives, but essentially you just need to remember them. So sine of x always goes to cos of x. Cos of x always goes to negative cos of x. So these ones are pretty easy to remember because they lead into each other. So sine x always goes to cos of x, which cos of x in turn goes to negative cos of x. Cos of x, in my opinion, is especially easy to remember. Now we have a little bit of an outlier here with tangent x, and that is because, well, normally with trigonometry, they teach you SOHCAHTOA, right? So you have sine, cosine, and tan, right? Those are the three trigonometric functions that you learn. But with tan, it's a little more complicated because with tan here, it introduces a more complex trigonometric function. So tan x isn't really as easy to remember as these two, but you just got to remember it. So tan x goes to secant squared x, or tan x goes to 1 over cosine x times 1 over cosine x, if you want to break it down that way, because that's what secant is equal to. All right, so here for example 1, we have f of x equals x cubed plus 2x. Now this may look a little familiar because that was our original function, right? So let me show you how we can just jump from x cubed plus 2x to 3x squared plus 2.
Okay, so here for our first example, we have, as I said, f of x equals x cubed plus 2x. So here's what we're going to do. Now remember what I told you about n times x to the nth power minus 1. So what we're going to do is we're just going to ignore this 2x right here for right now. So we're going to go 3x, right? That's our exponent. So now we need to do the n minus 1. So then that 3 minus 1 equals 2. So we get 3x squared. Now let's move on to our second term here, which is the plus 2x. Now, x, since it is just x, right, it's not to a power, it is technically to the first power here. So what we're going to do is we're going to go 2 times 1, right? So we're going to go plus 2. Now it is times 1. So times 1. Now this goes to x equals 0. Now x to the, not x equals 0, x to the 0 power. Now x to the 0 power also equals 1. So x to the 0 power equals 1. So what we end up with is 3x squared plus 2 times 1 times 1. Now obviously that 2 times 1 times 1 just equals 2. So we end up with our final answer, which is 3x squared plus 2, which is the exact same thing as the answer given to us by the limit method. Now, as you can see, this is much faster. Obviously, I oversimplified things like crazy here just for you to get the idea. But as you go through these, you won't have to do this step and this step. You can just do it in your head, essentially. Now, let's go back to the PowerPoint.
Okay, so here for example 2, we have a fraction. We have f of x equals 1 over x squared. Now, you're probably thinking, I have no idea how to deal with fractions. But don't worry, there's another simple trick that I will show you. So, if we look over here.
Okay, welcome back to my whiteboard. Now, so here is the trick that I was going to show you of how to handle fractions like this. So 1 over x squared is actually equal to x to the negative 2. Now this is something that you might remember from your early algebra days, or maybe not early, but from algebra anyway, and that is that negative exponents result in fractions. So x to the negative second power is the same thing as 1 over x squared. So then, once we have this, we can just do the same thing that we did in the last example, which is we're just going to get this, right? So negative 2, we're going to pull that out front, right? So we have negative 2x. Now, x to the negative second power, so n minus 1, n being negative 2. So negative 2 minus 1 is going to result in negative 3. Now, this looks a little funny, right? And a lot of people don't really know how to handle negative exponents. So, in order to make this simpler, we can go back to fractional form. So this will be negative 2 times 1 over x to the third power. See, these two things are equal, and we can take this even a step further by going equals negative 2x over to the third power.
Alright, now on to example 3. We have f of x equals 2 over 7x to the 4th power. If we look back to the board, or sheet of paper in my case, I will show you how to deal with this.
Okay, here for example 3, we have something that looks very confusing at first glance, right? So we have 2 over 7 times x to the 4th power. But again, we can break this down just like we did the last equation. Now, it's not quite as simple because let me show you another little trick here. We have 2/7, right? Now, 2/7 is really just a constant. So what this really turns out to be is 2 over 7 times x to the negative 4th. See, we don't really care about this 2/7 because it's just a number. Now, this isn't a constant in the sense that we can turn to 0 because it is being multiplied by the variable. What we're going to do is we're going to leave the 2/7 alone, right? We're only worried about x to the negative 4th power. We're just focused on this. We're going to completely ignore this, and we're just going to focus on this. So we get negative 4x, and then n minus 1, right? So negative 4x to the negative 5th power, or negative 4 over x to the 5th, right? So now you're wondering, well, what happens to our 2/7? Well, now we can bring that back in. So now we can go like this, times 2/7. So this should equal negative 8/7 x to the 5th power.
So here, for our 4th and final example, we have f of x equals x squared minus 4 over x cubed. Now, this is essentially an amalgamation of everything that we have been going over. So, I want you to try to pause the video and solve this on your own, and then come back, and then I'll show you how to solve it.
Now, I said this was going to be our 4th and final example, but I lied because I want to do one more after it just to clarify a little bit more of the constants from the last example. But let's carry on with this. So, you should have a pretty general idea of how to do this, right? So let's go through the same thing again. We're going to ignore the negative 4 over x to the 3rd power, right? So we just have x squared. We're not paying attention to this yet. So we're going to go 2x to the minus 1, right? So 2 minus 1 is 1, so x to the 1st power. Here, I'll write it here. Now we have this constant. So this can actually turn into this, so 4 times x to the negative 3rd power, negative 4, sorry. So x to the negative 3rd power is going to turn into negative 3x to the negative 4th power. Now, if we multiply back in our negative 4, we get 12x to the negative 4th power, or we have 12 over x to the 4th. So now if we get this, we can bring this back over here, so we have 2x to the 1st power plus 12 over x to the 4th power. Okay, we're just going to do a few quick bonus examples to help clarify a little better of how constants work. Okay, so let's say we have f of x equals 5, right? So in this instance, right, 5 just goes to 0. So this turns into f prime of x equals 0, right? Makes sense. That was the original rule that we laid out. So let's say we have f of x equals 10 plus x, right? And I showed this a little earlier, so this would actually just turn 10 goes to 0, right? So f prime of x equals 0 plus, now x to the 1st power, that just becomes 1. F prime of x equals 1. Because our 10 cancels to 0, and x goes to 1. So you should have an idea of how to find the derivatives of functions a little bit faster now. Now these get a little more complicated when you bring in things such as product rules and quotient rules, and you can do chain rule, but we're not going to talk about that in this video. And this should just help you to kind of get through your problems faster than doing the same old limit method. But we didn't get to any trigonometry problems, but it would be the same principles, very straightforward, right? F of x equals sine of x. What does sine go to, right? So f prime of x equals cos of x. It's pretty straightforward. It's very similar to all the other problems that we have here. But yeah, I think that's it, guys, and thank you for watching.